I'll leave example 3 as a exercise for you to try for yourself. But let's go ahead and just wrap up why derivatives are useful, and let's look at an example of when a function might not be differentiable. And we'll look into an example based on the absolute value function and how its derivative works. But just to sort of summarize, derivatives are useful for many, many reasons. First of all, they give us what we call the instantaneous rate of change, aka the slope of any mathematical function at any point in time. So another term for rate of change is speed or velocity. So say, for example, a graph tells me my current position, like on Earth. Basically, if we figure out the derivative of my position function, the derivative of that will give you what's called a velocity function, basically how fast am I moving at each point in time. So and this is a very principal idea in physics. If you've ever had physics before, calculus is important because if I have position and velocity are related together, because velocity just means speed, rate of change, how fast am I moving, which is related to where I'm at. And additionally, acceleration is related to velocity based on a derivative level as well. And this is all more to come in chapter 2. Chapter 2 is all on applications of derivatives. But it allows us to compare growth rates. Basically, what is the current slope? The slope tells me the speed of how fast something is growing. If I find a positive derivative, it means it is getting larger, it is growing, it is going up to the right. Whereas if it's got a negative derivative, it's going down. And again, as I said this before, but a zero derivative is also very useful to know because it implies it is not changing, it is constant at that point in time, which allows us to determine minimum maximum value. So all of this algebra that we have been doing can feel a little tedious and difficult sometimes, but the payoff is very, very strong. It's the basis of calculus. The derivative is one of the fundamental operators in calculus, and really important. That's kind of what I'm trying to say here. And so to answer another question, do all functions have derivatives? I think I've already said this before, but the short answer is no, not all functions can be differentiated, and sometimes they don't work. And I wanted to kind of look at what sort of cases that would happen in. So since the derivative is always, by definition, the limit as h approaches 0 of the difference quotient, that will straight off not work if the limit is undefined, or if the function has elements of the domain that are missing. So basically, if the function doesn't work, the derivative won't either. And also at the same time, if there ever is a limit, if the function has a point of discontinuity, that implies the limit doesn't line up with the function value. It will also not have a derivative at that point either. But actually, even continuous functions may have points where they're not differentiable, and that always happens on curves which have a very specific behavior. Actually, let's return to the page on discontinuity from a week or two ago. But if you remember, we looked at a couple examples of curves which were continuous, like these two, and then other examples that were not. Well, so anytime a function has a point of discontinuity, like a break or a hole or a break or a jump or whatever type of discontinuity it might be, it would not be differentiable at those points because their limits will not exist. So straight off the bat, we know that these three functions are not differentiable. Now, they are differentiable sometimes, like on certain intervals, but they're not differentiable purely. And that's kind of like with continuity. Sometimes some functions are continuous everywhere. Some have point discontinuities or specific values at which they're not continuous. It's the same thing for differentiability. Some functions have certain points where they're not differentiable. Like also looking at this function, if ever a graph has what's called a cusp or a corner, basically like a sharp change in behavior like this one, it will never be differentiable at the point of the cusp. And really the simple reason why is if I was to ask you what is the slope at this point, you can pause the video and think about that for a second if you'd like. But the issue is, well, like for example, on the right part of this curve, you can tell it has a slope. It's got, in this case, actually it looks like the slope is about 45 degrees or 1. And over here, the slope is different, -1. If it ever goes from having for one slope to a different slope instantaneously, the question is, well, what is the slope at this point in time? is the slope best exampled by the left side or by the right side? Or is it somewhere in between those two values? Is it something like this? And that's the problem, is technically it has different slopes depending on where you look. It does not have a consistent slope, meaning that it is actually not differentiable at that particular point. And what this graph looks like, some of you may recognize, this is actually the graph of the absolute value function, which let's return back to look at the derivative or the example in the packet, which comes next. And also there's another case which a function may not be differentiable, in the case whenever it might have a vertical tangent line or a slope. Technically a vertical tangent line, we sometimes say it has a slope equal to infinity, but you can't write an equation of that line, and there's problems with that. We'll revisit that idea later. But looking at the definition of the absolute value function, basically we could take the derivative of a piecewise function by looking at the derivative of each piece separately. Basically take the derivative on each point of the domain. And so since this is a linear function x, its derivative will be equal to its slope, which is just 1. So you can basically, what you could do here is you could apply the definition of the derivative to find the derivative of x. Actually, it's very easy. Let's go ahead and do that because it'll be really fast. But let's go ahead and say, well, what's the limit as h approaches 0 of this particular function? And basically, we need to do each piece of the function separately because each one will have a hypothetically different derivative based on each formula. But for the top one, we'd have, well, x plus h minus f of x, which is just x divided by h. So since we would say f of x is just equal to x here, very easy to find the difference quotient. X minus x will cancel, and what will be left with is h over h, which is 1. And basically, since the slope of this line is 1, since it's mx plus b, and it's just 1 is the coefficient, it will have a very easy slope, or its derivative will be very simple. And this will be equal to 1 on the top half. And then on the bottom half, negative x, you could do the same exact thing, find by the difference quotient, calculate its derivative, but it would be negative x minus h, plus x, because again, it's always f of x plus h minus f of x. Here, if I plug in x plus h right there, I would get negative x plus h, which would distribute to be negative x minus h. Then it would be minus f of x minus the original function. Minusing a negative always makes plus x, and this would all be divided by h, which would give us cancellation once again. Here I'd be left with negative h over h, which is negative 1. But essentially, the slope of that line would be negative 1 instead. And again, looking at the graph of the absolute value function, it looks exactly like that. It has that sharp corner at x equal to 0, where it's not differentiable. We can see that the slope is different in each particular case. And again, you could say, well, this function, it said that it was defined for x is greater than or equal to 0. So, but for the derivative would not, at x equal to 0, the limit as h approaches 0 has to be the same from both sides. And what I can see here is the limit as h approaches 0 from the right-hand side is equal to 1, because I would be using this particular thing. So, I'll go ahead and be more specific here. This would be the right-handed limit. This would be the left-handed limit of f of x. Those limits do not agree, and we know that when the limits do not agree, we would say that the general limit as h approaches 0 of f of x does not exist. And since that limit does not exist, we would say it is not differentiable at 0. So if I wanted to be more specific about the derivative function, we would say, well, when x is greater than 0, the derivative is equal to 1. When x is less than 0, the derivative is negative 1. But when it is equal to 0, the derivative does not exist. So we would say that f of x is not differentiable at x is equal to 0. And what I recommend is if you're looking for when a function is not differentiable, it will usually happen at either points such as the domain, it does not exist, or a piecewise function where we have a switch in domain. And there are some other cases that are a little bit more rare. We will look at those when we visit those later.